SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 59. We are discussing about design of transonic compressor. So in last few lectures we were discussing about design of transonic compressor with different configuration in sense of flow tracks. So we were discussing as transonic compressors are mainly high pressure compressors and per stage pressure ratio, that's what is very high, and that's the reason why the flow, that's what will be coming out at the exit, that will be having higher pressure. That means its density also will be higher, and in order to satisfy the continuity equation, assuming our axial velocity to be constant, my exit area will be coming to be lower. And for that we have discussed about three different configuration. One we have discussed as a constant tip diameter, constant hub diameter, and third approach we have discussed about assuming some radius ratio. Now what all design methodology we have adopted for transonic compressor with two configuration, constant hub diameter and constant tip diameter, where we have discussed about the fundamental design approach. At the same time we have discussed, like as per the requirement, when people they are doing their transonic fan design, that's what is having somewhat different approach, and that's what is the most recent approach. So we should explore that possibility in this subject, especially with the interest. So let's move towards that part. So what we have realized, if we consider we are having say vortex flow, that's what it say, Cw into r to the power n equal to constant. So for most modern design, people they are changing their load distribution at the mid span, they are changing the load distribution at the tip and near the hub region. So what exactly they are doing, say near tip and hub, the design it is say offloaded design, where these exponents, that's what is been taken as n equal to 2. We can say this is what is helping in order to reduce the end wall losses, mainly say near the tip region, that's what is reducing your tip clearance losses. At the same time at the hub or near the hub, that's what will be reducing hub corner losses. Now at the mid span, in order to compensate what load we will be losing near hub and tip, that's what will be getting compensated at the mid span region, where this exponent, that's what has been selected as n equal to 0.8. Now this is what is giving the flexibility in order to reduce the losses, and that's what will be improving the efficiency. One other criteria, that's what is a wider operating range, and in order to operate our compressor or in order to have wider operating range under off design condition, some design strategies need to be modified, and that's what is depending on say kind of experience the designer has and what all are the strategies they have been decided by engine manufacturing company. So for particular organizations, they are having certain rules and they are following certain laws in order to design those transonic compressors and fans. So what we have learned from that, let's try to take one of the numerical. What it says, the fan of low bypass ratio turbofan engine is required to operate at the pressure ratio of 2 and has mass handling capacity, that's what is 55.6 kg per second. The outer diameter is limited to 1 meter and inlet hub to tip ratio is 0.35. So we can say these are the constraints. So we should not exceed our casing diameter beyond 1, and at the entry we are having hub to tip ratio to be 0.35. It is required to design the fan with loading gradually decreased near the hub and tip region assuming constant axial velocity throughout the span. Air enters the rotor at a temperature of 59.6 Kelvin and pressure of 37 kilopascal. This is what is, we can say, low bypass ratio engine. That's what is mainly been used for, say, fighter aircrafts, where we are doing design. So many times the designer, they are preferred to go with cruise condition. So this is what is a cruise condition, we can say. The rotor rotational speed must be kept under 8000 rpm based on the turbine rotational speed, and preferred to have Mach number should not exceed by 1.4 near the tip region of the blade. So in overall, if we look at what we are planning to do is the design of, say, axial flow fan for low bypass ratio engine. That's what is having, say, compression ratio in the range of 2. That's what is slightly on the higher side. We can say entry pressure and temperature, they have been defined under the cruise condition. Mass flow rate is given, that's what is 55.6 kg per second. And what it says, my casing diameter should not exceed by 1 meter. Rotational speed also is constrained by 8000 rpm, and it says my axial velocity that need to be constant. So we must realize, actually, by changing our wall distribution or load distribution, we are violating the law of radial equilibrium. So as we have discussed earlier also, for many times, especially for axial flow fan design, this violation, that's what is been valid, and people, they have done design, and those designs, those fans are working fine, absolutely fine as on today also, and that's what we are opting here. So let's try to have solution for this. So what all we know is my size and speed, that's what we need to estimate. Okay, we need to do our design at 75% of span, because this compressor, we can say, that's what is a transonic compressor, or we can say this is what is transonic fan. Now we are looking for different velocity components and velocity triangle in order to determine the components like axial velocity, peripheral speed, relative velocity, absolute velocity, different flow angles. All those things, those need to be calculated at different stations. So initially we will be doing our calculation at the mid station, and then after we will be applying our low. Here in this case, we are not opting for, say, straight free vortex design or straight force vortex design, or maybe fundamental design. So that's why it is named as a control vortex design. So let's try to understand what exactly is the meaning of that. Now, as we know, at the entry condition, we need to have our entry dimensions. Now, in order to have those dimensions, we must know what will be our entry density. At the same time, we are looking for, say, axial velocity as well as peripheral speed also need to be known in order to complete our velocity triangle. So what we will be doing, let's say for this case, we are assuming our axial velocity, suppose say 150 meter per second, and nothing it is mentioned. So we will straightway say at that particular station, or say we can say our entry, that's what is, say, axial entry. That means my CA and C1, they both are same. If we are putting that, that's what is giving me my entry temperature as, say, 248.4 Kelvin. Now we know what is our entry pressure, what is our entry temperature. So based on that, we can calculate our static entry pressure, and that's what is coming, say it is 31.70 kilopascal. Now these things, that's what is already been discussed in so many cases. That's the reason we will not be taking much time in explanation. Here we can say we can calculate our density based on our static pressure and static temperature. That's what is coming to be 0.44 kg per meter cube. Now once this is what is known to us, we know our continuity we can write down. That is nothing but it is in sense of, say, my density into area into, say, axial velocity. Here in this case, at the entry, my hub to tip ratio, that's what is given. it is 0.35. So based on that, if we are assuming our tip dimension to be 0.5, it says my mass flow rate, that's what is coming, 45.9 kg per second. Now this is what is less than what mass flow rate we are expecting. So we need to realize if my entry mass flow rate, that's what is low, that's what will be reflecting in sense of my thrust generation capacity for particular engine. And that's the reason why we can say this is not acceptable mass flow rate at this moment. That means what axial velocity we have assumed, that's what is say on a lower side. So let's try to take our axial velocity to be say 200 meter per second. If we are taking that to be 200 meter per second, we will be having our temperature, static temperature, it is 239.69 Kelvin. We can determine our pressure, static pressure, that's what is coming, say 27.98 kilopascal, and we can calculate our density. This density is coming 0.406 kg per meter cube. Now if we will be putting this in our mass flow rate equation, that says this is what is coming as say 55.96 kg per second. So we can say this is what is in acceptable range. Now this is what is very important when we are doing our assumption for axial velocity. We have discussed in earlier numerical also, sometimes we need to assume with the axial velocity. Many times axial velocity may be known to you, maybe flow coefficient is known to you. All those design strategies we have already discussed. Now based on that, we need to define with what need to be my peripheral speed. Okay, so in order to have that peripheral speed to be calculated, let's assume say my tip peripheral speed as say 370 meter per second. If we are taking that, my rotational speed is coming 7066 rpm. We can say that's what is say near to my 8000 rpm. So at this moment, let's put that as a number. We need to check with our relative Mach number at the tip, and in order to do that calculation, we need to calculate our relative velocity. If we are calculating our relative velocity, that's what is coming 420.56 meter per second. Our sonic speed, that is 310.33 meter per second. So we can say the tip Mach number, that's what is coming 1.36. We can say that's what is less than 1.4. So this number, that's what is acceptable. So we can say now we are fixing with our axial velocity, we are fixing with our peripheral speed. So like many times based on certain assumptions, you can go forward with. It says it should not exceed by 8000 rpm. You have that flexibility. You can assume the speed to be say 7500 rpm and you can do calculation. There is nothing wrong in that. So this is what is based on few of our iteration, and that's the reason why we are straightway putting our peripheral speed as say 370 meter per second. So based on that, we can say we are finalizing our axial velocity, that's what is 200 meter per second, and it is given, that's what is constant throughout my span. And our peripheral speed we are considering 366.52 meter per second. Rotational speed we are considering 7000 rpm. If this is what is known to us, so at the entry condition we can say we are having our parameters known for making of a velocity triangle. Now this is what is a fan, that's what need to be designed. So if we consider this is what is my entry condition, we can say that as a station 1, and this is what is my exit condition, we can say that as a station 2. Now here in this case, in order to calculate my exit dimensions, we know what is our pressure ratio. So our pressure ratio given, that's what is say 2, and based on that we can calculate what will be our total pressure at the exit. Now this is what we will be using in order to calculate our delta T0. That is nothing but my total temperature rise across my rotor, and that's what is coming 63.17 Kelvin. Now from the known parameter, if this is what is known to us, we can calculate what will be our total temperature at the exit. Since my T01 it's known to us say delta T0, that is also known. So we can say T02, that's what is coming 322.77 Kelvin. Now what it says, like we have considered, or it is known, say axial velocity, that's what is say 200 meter per second. So we will be putting and taking that as same. We are considering, say assuming say exit to be axial in for the sake of simplicity we can say. So for that we will be calculating our exit temperature, and that's what is coming 302.86 Kelvin. Now once this is what is known to us, we can calculate what will be our static pressure at the exit, and that's what is coming 59.21 kilopascal. Now once the static pressure and static temperature they are known to us, we can calculate our static density, and that's what is say P2 by RT2, that's coming as a 0.68 kg per meter cube. Now in order to calculate our exit dimension, we will be taking help of our continuity equation. So from this continuity equation at the exit system, if we are writing, that's what is nothing rho 2 into A2 into axial velocity. So this A2, that's what we are representing in sense of hub to tip ratio at the outlet. So if we are considering this as a case, we will be first calculating what will be my hub to tip ratio at the outlet. Now this is what is a fan, that's what we are designing to be on say safe side, or we can say we can straightway assume constant tip kind of configuration. There is nothing wrong, you can move it even constant hub also, even you can go with say constant mean diameter configuration also. But we can understand at the entry condition it is most preferred to go with say constant tip diameter. Here the expected pressure ratio is in the range of 2. That is also giving one of the indication for selection of constant tip diameter configuration. So if we are considering constant tip diameter configuration, we will be getting our hub to tip ratio at the outlet, and that's what is coming as say 0.69. Now here in this case, once the hub to tip ratio at the outlet station, that's what is known, we can calculate what will be the hub diameter or hub radius at the exit, and this is what is coming as a 0.345 meter. Now in order to do our calculation at 75% span, we need to have our mid station. So if we draw our inlet area and outlet area based on the radius, we will be getting our 75% span like this. So we need to calculate what will be our R1 mean and what will be our R2 mean. So that's what is been calculated based on 75% span. So my mean radius at the entry, it is coming 0.418, and at the exit, that's what is coming 0.461. Now we need to be very careful here, since my peripheral speed, it's a function of my diameter, and that's the reason why my entry peripheral speed, that's what need to be calculated based on entry radius, and that's what is coming 306.41 meter per second. Same way for outlet, it is coming 337.93 meter per second. Now very important configuration or very important discussion, that's what is coming here. What is our case? Say we want to do our design, that's what will be based on say control vortex kind of configuration. Say it has been asked like we need to lower the lower say rotor at hub region and near the tip region. In order to lower that configuration, we need to change certain parameters. We can say my loading or work done capacity, that's what is a function of my say whirl component. So if you will be able to manage my entry whirl component and exit whirl component, we will be able to reduce the loading near that region. Now in order to do that configuration, we need to have value of delta P0 at the mid station. At the same time, we need to have certain known parameter, that's what is suppose say degree of reaction. Now here in this case, my degree of reaction, that's what is not given. So what we will be doing, we will be assuming our degree of reaction at 75% span. Based on our fundamental understanding, we can calculate what will be our entry wall component and exit wall component, and that's where we will be applying our control vortex law. So let's move how exactly we will be checking with. Now here there is nothing mentioned in sense of what need to be the number of say my wall component or my loading component. That's the reason why we need to keep on eye for parameter say degree of reaction. We can understand if we are reducing our load near the hub region, there may be possibility that my degree of reaction will be going low. It may be going 0 or sometimes it may go negative, and we know consequences for that. And that's the reason why we need to keep an eye for that degree of reaction near that hub region. Same way we will be taking care of my blade angle variation. We can say metal angles beta 1 and beta 2 variation, or we can say delta beta variation, that need to be smooth. Okay, so for that let's see what can be done here. So when we say we need to assume our wall component at the entry and wall component at the exit, that's what we will be calculating based on assuming degree of reaction. Now throughout the span we need to vary our wall component at the entry as well as exit. So what we have learned in week 3, we have certain possibility. It says we can assume arbitrary wall velocity distribution. Say we will be taking say CW1 equal to AR to the power n minus B by R. We can consider CW2 as say AR to the power n plus B by R. It says like maybe at the entry you can consider this as a negative sign, at the exit you can take that as a positive sign. Now this exponent we already have discussed. When we are configuring n equal to 0, we can say it's an exponential design. If we are considering n equal to 1, that's what is my constant reaction design. If we are considering a equal to 0, that is nothing but it is a free vortex design. If we are considering b equal to 0 and n equal to 1, that's what will be force power design or force vortex design. Now there are ample of possibilities here. So it's a designer's choice how he or she will be deciding the distribution of wall component at the entry and the exit. What we will be doing here, say in order to simplify and in order to reduce our calculation and for understanding, we will be configuring our say span of the blade into 3 different stations. We will be considering my first station, that's what is from hub to 40% of span, then from 45 to 85% span, and above 85% span. Now what it says, we need to load our hub and tip in order to have proper distribution or in order to have lower loading in that particular region. Now in order to have that kind of configuration, we will be assuming say from hub to say 40% of span, my distribution will be CW into R square equal to constant. In say mid span region or say from 40% to 85% span, we will be taking CW into R to the power 0.8 equal to constant, and from 85% to tip we will be taking CW into R square equal to constant. Now this is what is very important, we need to realize that part. So you can say this is what we are looking for in sense of our distribution. Okay, we are expecting our total pressure rise of 2, or we are expecting our pressure ratio of the 2. So it says in this particular region we will be loading on higher side, near the hub region and near the tip region we will be loading slightly lower. This is what is very interesting, and this is what is now the design concept which people they are adopting these days. So if we are configuring this, there are other chances also. The question may come in your mind, sir, in order to change this CW, we have different possibilities with us. One, that's what I have discussed, that maybe you can assume say some Cw into the power into r to the power n equal to constant. That's what you can assume. Second possibility, that's what is, you can take fundamental design approach where you will be having your delta P0 distribution, but this is what we have discussed for many approaches. So at this moment we will not opting for this configuration. Now there is one more possibility. Many designers, they are changing the axial velocity from say hub to certain span location, and then after from say that particular span to higher span, they are configuring say higher axial velocity, and towards the tip region they are configuring lower axial velocity. So that is also possible. But here in this case what it says, my axial velocity, that's what is constant. So we will not be exploring that possibility. What we will be exploring is having the world distribution in the range of Cw into r square or r to the power 2 equal to constant from say hub to 40% span, and from 85% to tip region we will be taking Cw into r square equal to constant, and at the mid state region between say 40% span to 85% span we will be taking Cw into r to the power 0.8 equal to constant. Now the thing is, once this is what has been decided with us, the question will come, we need to have our world velocity component at the entry and our world velocity component at the exit. Then only we will be having that law to be applicable with. So what we will be doing, suppose say if we are considering we are having our aerodynamic work and we are having our thermodynamic work. So we can say aerodynamic work, that's what is giving us the world velocity distribution, say like Cw1 component and Cw2 component. So what we will be doing, say we will be calculating our delta T0 at that mid station, that's what is coming say 63.17 Kelvin. If we are comparing our aerodynamic work and thermodynamic work, assuming work done factor to be 0.98, we will be getting some distribution of say my world component Cw2 and Cw1. So this is what I am writing as a equation 1. Okay, so in this case we are not knowing what is our Cw1 and what is our Cw2. Okay, now say second configuration, what we will be doing is we will be assuming our degree of reaction. So this is what is a little tricky in that sense. If suppose say if I am assuming my degree of reaction to be lower at 75% span, there may be chances that near the hub region my degree of reaction will go even low, it may go to 0. So in order to avoid such kind of situation, let's assume say degree of reaction to be 0.68. So what we know, our degree of reaction, that's what we are correlating in sense of world components at the entry and exit and mean peripheral speed. So that's what will be giving us the equation in the form of Cw1 and Cw2. Now we are having two equations. One, that's what is from our say aerodynamic and thermodynamic work comparison, and second, that's what is based on our degree of reaction correlation. So that's what will be giving me Cw1 and Cw2 distribution at the mid span. Okay, so this is what we need to learn, this is what we need to understand. Okay, now we have discussed some of the numerical in week 3 for say calculation by using different laws. So if required, just go through, repeat those calculation, go through those slides again. That's what will give you brush up of your knowledge. Again you will be coming to the momentum for this numerical. Now once at the mid station, we know what is our world component at the entry and exit. We can make our velocity triangle, and from that velocity triangle we can calculate what is our flow angle at the entry, that's what is coming 2.18. My beta 1 angle, that's what is coming 56.18, and my beta 2 angle, that is coming 34.86. Now this beta 1 and beta 2, they are known to us. We can calculate what is our delta beta, and this delta beta is coming 21.31 degree. Same way we can calculate what will be our alpha 2. This alpha 2, that's what is coming 44.79 degree. Now we are interested in checking with some of the parameters. So in order to have those calculations, we will be calculating what is our relative velocity at the entry and what will be our relative velocity at the outlet. So if we are using our triangle law, and from that it says my relative velocity at the entry is coming 359.33 meter per second, and relative velocity at the exit is say 243.74, and that's what is giving a de-Hauler factor of 0.68. Now next important parameter for us, it is to select or to calculate the number of blades and chord. So what we will be doing in line to what all we have done, here also we will be assuming our aspect ratio. Let's say for this blade aspect ratio is say 1.6. If we are putting that aspect ratio as 1.6, we are able to calculate our blade chord, and that's what is coming as say 0.15 meter. Now once this is what is known, our next calculation, that's what is to calculate the number of blades. So in earlier numericals, what all we have solved, there we have assumed our diffusion factor, and based on that we used to calculate our number of blades. Let's take a different approach in order to understand and realize this calculation in a different way. We can assume, suppose say mean say S by C ratio as say 0.88. If we are considering that as say 0.88, we can calculate our number of blade, and that's what is coming 20.89. So safely we can consider that as a 21 number of blades. Here you may have argument saying, sir, why we are not assuming diffusion factor? Just understand one thing, we are having our keep on eye parameters like say de-Hauler's factor, degree of reaction, diffusion factor. So one of the parameter we already have assumed, that's what is our degree of reaction. So it is preferred not to go with assumption of second parameter also. That's what may give you very aggressive design. So in order to avoid that kind of situation, we are assuming our say S by C ratio or pitch to chord ratio as 0.88. If we are putting that as a number, the diffusion factor is coming 0.52. Now we need to calculate our blade parameter or say blade aerofoil or aerofoil geometrical parameter. That's what will be based on Carter rule. So we will be calculating our slope factor. Here this blade also we are considering as a circular camber line, that's why E by C is 0.5. That's what is giving me M equal to 0.34. My camber angle, that's what is coming 30.17. Here also we are assuming our incidence angle at the mid station to be say 0. We can calculate what is our deviation angle and what will be our stagger angle. So this calculation what we are discussing, those are the cascade parameters. The methodology opted for the calculation, that's what will remain same. Okay, and mean line calculation almost if you look at say that's what is coming as a similar kind of procedure. And if you look at the textbooks or if you are referring the books, people they are discussing about the mean line calculation, and then after they are putting say same way we can do our calculation for tip and hub. But we can understand in order to do systematic design, very particular design, we need to have more number of station. That's what will be giving us our blade to be in our hand as per our expected performance. Okay. Now this is what we are doing our calculation at say 75% of span. So these all are the parameters we are calculating. Now very next step, that's what is coming, that's what is to distribute our whirl component. So here in this case, if you look at from say 40% to 85% of span, we are considering our CW into R to the power 0.8, that's what is coming say constant, it is say C2 we are putting. Okay, same way any radius in between these two, that's what we can calculate. because we have done our calculation at the mid station 75% span. So we will be taking that as a constant, and that constant we will be applying between 40% span to 85% span. So this is what we can calculate in sense of CW1, that's what is coming 9.78 meter per second. Same way my CW2, that's what is coming 220.70 meter per second at 40% span. Now say below 40% span, we are looking for CW into R square equal to constant. So our requirement, it is to calculate the CW, or we can say that's what is say C3. The constant need to be calculated. So here we must realize at particular span, suppose say 40% span, we have opted for CW into R to the power 0.8 equal to constant. So at one station we cannot have say two different wall velocity components. So what we will be doing, say at 40% span, we will be applying the same law, okay, because this is what is known to us at 40% span. So that's what will be helping us in order to calculate C3. Same way we can opt for say C1 also near the tip region. Now when we are configuring our design, say that's what we have discussed here. So there may be chances near this 40% span as well as near the 75% span, we may be getting our distribution of wall component in a zigzag way. So we need to have smoothing of the curve in that particular region, and that's what is being done. So here if you look at, this is what is representing the distribution of say CW1 at entry from say 0 to 40% span, from 40% to 85% span, and from 85% span to tip region. So this is what is representing the distribution of CW1. In line to that, this is what is representing the distribution of CW2, and based on that, if we will be putting our I, and if we calculate our delta P0, this is what is representing the loading. Now here in this case, by changing the value of CW1 or CW2, even we are able to modify the tip loading. But at this moment, this is what is serving our purpose in sense of expected pressure ratio to be 2. So this is what is been calculated, and this is what is been assumed with. So you can say this is what is representing CW1, this is what is representing CW2. So we can understand we are having our Excel sheet program. For that Excel sheet program, we will be doing our calculation from 40% span to 85% span, and then after later on that same sheet we will be using for different wall distribution. And at the junction point, it may require we need to modify our distribution. Okay. Now let's look at this. This is what is representing the Excel sheet with having say smoothing of the curve. So if we look at, this is what is representing very first calculation, that's what we have done at 75% span. Same way, this is what is representing the calculation at 85% span, and this is what is representing our calculation at 40% of span. Okay. Now we are putting our I in order to understand say what is the variation of delta P0, because that is also very important for us. Same way we will be putting our I for say degree of reaction. So if we look at my degree of reaction at the hub, that's what is coming 0.48, and near the tip, that's what is coming 0.74. Now diffusion factor, that's what is varying all the way from 0.19 to 0.56, and we are having our variation of camber angle and stagger angle accordingly. So we need to check with what is happening with all these parameters in line to what all we have discussed up till now. So this sheet what we are observing, that's what has come after many iterations. Okay. So likewise, when you are doing your design, you need to be very careful. It is not that you are sitting for an hour and you will get the design. That's what is required, lot of parameters to be observed. and those observed parameter again we are putting with the highlighting point. That's what is say delta P0, delta beta, degree of reaction, diffusion factor, de Holler's factor, camber angle, all those parameters you need to keep an eye. Now, based on what all calculation we have done, this is what is a blade, that's what is coming. So here if you look at, this is what is representing my curve at the hub, and this is what is at the tip region. And in this case, if you look at, this is what is my hub region and this is what is the tip region. And in three-dimensional way, if we look at, this is what will be the shape of our blade. So now if you look at this blade, you must realize what all blades we are looking for, high bypass ratio fan or say low bypass ratio fan, that's what is having three-dimensional funny shape. And just realize that shape, it has come by design. Just understand that thing, it is not because it looks nice, but this is what has come by design. Here in this case, we are not discussing anything about the variation of chord. We are assuming our chord length to be same throughout the span. It may be possible designer may modify the chord length near the hub region, maybe at the mid station and even at the tip station as per the requirement. So now once you are making this blade ready with, use your computational tool in order to simulate this blade. Once you are simulating your blade, just observe certain parameters what we are looking at in sense of say increasing the losses or decreasing the losses, or how my flow, that's what is behaving on suction surface, how my flow, that's what is behaving on pressure surface. Based on that, certain modifications you need to do, and after doing those iteration you will come up with the final design. That's what it says. This is what is working fine under design condition. It may be possible when you are doing your design, that's what is giving best performance, expected pressure rise, even efficiency at a design point. But when you are putting that under off design condition, suppose say 80% mass flow rate or 75% mass flow rate, you will find that's what is not giving wider operating range in sense of my stall margin. Under that condition, you may need to modify your blades. You may need to modify your aerofoils. If possible, you may need to modify your dimensions of the blade. So this is what is all we are discussing in sense of transonic compressor. So in overall this week, if we configure week 10, that week 10 we have dedicated for design of transonic compressor, and in that we have discussed detailed design of transonic compressor. That's what will build the confidence in you for designing the future axial flow compressor or future axial flow fan which are of transonic nature. So here we are stopping with. I'm sure you will get the confidence. It is preferred that you just make your own design sheet, do this calculation, what all design we have done. You can go with some other configuration also. Say configuration like maybe you can go with the free vortex, you can go with say different loading, and as we have discussed, you can go with change of axial velocity. And that's what will be giving you the feeling of real design. Thank you very much.